Hello everybody, and welcome to the second ever Spruce and Jamie collaboration. The first being Spruce and Jamie's Aquarium adventure, released in 2017. Link in the description. This time we'll be focusing on something a little bit more educational. And that is birds. Well, not exactly birds. Birds are kind of boring. No offense, James. Instead, we'll be looking at the way that birds flock. If you've ever seen birds flocking, it looks completely chaotic, but that's actually far from the truth. In the late 1980s, a very smart man by the name of Craig Reynolds came up with a system of modelling how birds flock. Reynolds said that there were 3 rules that each bird tries to follow which create the flocking behaviour. The first, and probably the easiest to understand, is separation. Each bird is trying to stay a good distance away from every other bird to avoid crashing into each other. The second rule Reynolds came up with was alignment. He said that each bird was trying to match the direction and speed of all the other birds around it. And the third rule was cohesion. Each bird tries to stay fairly close to all the other birds. And at first, the rule of cohesion would appear to be completely against the first rule, which was separation. But it's actually not. With the rule of separation, the bird only focuses on birds close to it, because only birds close by are at risk of crashing into each other. Cohesion focuses on a much larger picture. Reynolds called his model the Boids model, and that's what I'll be calling birds for the rest of this video. So let's have a go at coding this in 2 dimensions first.
So the project deadline is tomorrow, and Mr. Beverly, we've been working on this for over a term.
The first thing I did was give every Boid a random position. Then I told the computer to draw a dot at every position where a Boid was. And this works, but we need to give the Boids motion. And there were lots of different ways of approaching this, but the way I did it was to tell the computer to give every Boid a random velocity. Then, because velocity is just the change in distance over time, I could tell the computer to just continually add the velocity to the position to get a new position, and then draw that new position. So I run this code and I can see that every dot moves at a constant speed in a straight line. And the problem here should be immediate. Eventually, all the Boids are just going to go off the screen. So to fix this, I write some code which effectively wrapped the screen around itself. When a Boid reached the top of the screen, I set its Y coordinate, or the height, to the bottom of the screen. If a Boid reached the bottom of the screen, I just did the opposite and set its height to the top of the screen. And I did exactly the same for the width. So now I have a baseline model. Let's start adding some rules to make these little dots behave like birds. The first rule I chose to code was alignment because it's the easiest and I'm lazy. Reynolds said each Boid can only see the Boids closest to it. So to do this in code, I have to make another variable called vision. Then, for every Boid, I pick a random Boid around it and I calculate the distance between it and the original Boid. If that distance is less than my vision, it means that the Boid is able to see it, so it wants to align with it. Then, once I've found all the Boids that this one Boid is able to see, I take the velocity of all the nearby Boids and take an average of it, so that I have an average direction of where all the Boids are heading. Then, I imagine that in an ideal situation, the Boid wants to immediately switch its direction that it's heading to that average direction where all the other Boids are heading. But obviously it can't do that because it's already heading in a different direction. So the way I deal with this is I imagine that the ideal velocity and the current velocity of the Boid are 2 forces trying to pull the Boid in different directions. So I need to calculate the overall force which is acting on the Boid. But because velocity is a vector, we can just subtract the current Boid's velocity from the velocity that it wants to have, and we get an overall force that is acting on the Boid. To keep this simulation realistic, we have to limit the force which the Boid is able to take. Because in real life, if too much force is put onto a bird, it would die. Then I looked at the equation force equals mass times acceleration. Because all the Boids have the same mass, I can just forget about the mass and I get the equation force equals acceleration. So I can take this overall force and just make it into acceleration. Then all that acceleration is just how much the velocity is increasing over time. So if every frame I calculate the overall force that is acting on the Boid, then convert that into acceleration, and then add that acceleration to the velocity, I get a new velocity which I can then add to the position to get the position that the Boid is going to be in next frame. So we run this code and we can see that fairly quickly all the Boids start to head in the same direction at the same speed. The next rule that we have to focus on is cohesion. Cohesion is where all the Boids try and share an average position. And I coded this almost exactly the same way as I did the alignment rule. I found all the Boids that one Boid was able to see. Then, instead of adding up all of their velocities, I added up all of their positions and took an average to get the average position of where all the Boids were. Then we need to convert this average position into a velocity so that we can calculate an overall force acting on the Boid. And the way that we do this is because I've coded position as a vector, I can just subtract the current position of the Boid from the average position of all the other Boids, and I get the velocity the Boid would need to take to get to the average position of all the other Boids. Then we can just do the same as before, calculating an overall force that acts on the Boid and converting this into acceleration. However, this time we've got two accelerations acting on the Boid. We have the acceleration that we just calculated, and we also have the acceleration from the alignment rule. However, this is really easy to deal with. We can just add the accelerations together to create an overall acceleration. So we run this code and we can see that fairly quickly all the Boids come together in a single point and all start heading in a single direction. So the code works, but this is clearly in need of the final rule, which is separation. And again, this is very similar to the rules before. All I do is find the Boids which are able to be seen, then I take the position of one of the Boids which is able to be seen, and subtract the position of the Boid that I'm trying to calculate the acceleration for. And this gives me the velocity which I would need to go straight towards that Boid. But I want the velocity which allows me to go away from that Boid. So all I do is I take the velocity which I would need to go towards that Boid and make it negative. Then I calculate the negative velocities of all the other Boids that are able to be seen, and I take an average of that to get the velocity that would take this Boid away from as many Boids as possible. Then I do the same as before, taking the velocity that would be needed to get away from as many Boids as possible, and the current velocity of the Boid, and calculating a force from that. Then calculating acceleration to calculate the new position of the Boid. So we run this code with the final rule, and we can see that the dots behave like flocking birds. But there's one thing I don't like about this model. I'm not able to see the direction that the Boids are heading in very well. And this was actually a really simple fix. All I did was replace the dots with a triangle. I also added some sliders, which increase and decrease the force that each rule puts on the Boid. And this allows the user to see how each rule changes the flocking behavior of the Boid. However, this is only a two-dimensional model. I'm now going to pass over to my fellow colleague and esteemed game designer, Spruce Campbell, to tell you how he made a three-dimensional bird flocking model using the same rules and methods as I did to make this 2D model.
Wow, Jamie, Boids in 2D sounds like a pretty dead meme to me. See, by this point I'd already designed a kind of flocking simulation called Starlings last year, but I'll let you know a little secret. It wasn't actually flocking. So I thought this year I'm going to update it, I'm going to revamp it, I'm going to redo it, and I'm going to do it in 3 dimensions. With this in mind, we were going to make the best Boid simulation there ever was. So what are you waiting for? And we opened up a new project right now.
So,
Uh-oh.
Wait, no, that's actually flocks though.
Yeah, it's not great, is it? The problem was, the more features I wrote in, added in, and I changed bits, they didn't really get any more flocky. They just got angrier, and it got worse and worse. By the end of it, when I'd actually put in all the Boids rules, they all just kind of flew around like angry bees. The problem was, I had a bird, right, and I was applying different forces based on different rules, and it was just kind of jerking the bird around in random direction, and I thought what I actually needed to do was focus not on the forces, but on the rotation. See, instead I would have a bird, I would have a direction it wanted to go in, and then I would see what I'd have to rotate it by to get it going that direction. And the key thing is that the bird is always moving forward. So I thought it was time for a bit of a rework. I opened up Blender, made a thing, added a bit of wobble to how it flew. I could see it going across the screen, and it looked quite nice. So now, all that was left for me to do was to put in the 3 rules of Boids. Separation, I defined as the direction to get away from each nearby Boid divided by the distance to each Boid, and the sum of that. And you can see, if we draw the lines between each Boid, you can see that the more crowded they are, the more they want to get away. Alignment was just the average angle of all the nearby Boids, and after I got these 2 in, got something resembling a flock there. Finally, cohesion, which was just move into the average position of all the nearby Boids, which I think looks pretty nice. The only problem was this weird popping in and out effect. This was caused by the wrapping I was using. See, in 2D, wrapping's quite easy, but in 3D, you can't really make it work without it looking weird. So I had to add a 4th unofficial force, which was move towards the middle if you are far away from the middle, you stupid bird. Whew. And it works. Oh, what a lovely day! So from here on out, it was basically just polishing. You know, maybe whack a bit of a UI in there. Maybe get rid of this stanky ass sky. No, that's even worse. Paint up a quick little sky and we're good to go. Then one more UI pass. Looks pretty good. Just upload that bad boy to the internet and we're ready to go. What's this? Jamie? Jamie's complaining? Complainy? There were unfortunately some problems with this. If you orbited the camera anywhere near the poles, it would just get stuck in this disastrous loop. And this was because of gimbal lock, which you can learn about by clicking on this video.
No, you can't.
What?
YouTube disabled the annotations feature like years ago. You have to click on this eye thing now.
Alright, nerd. Also, the goal slider didn't do much, so get rid of that. Maybe put it all up and add a menu hiding button, maybe. What is this, luxury? What are we in the Empire? Is this the Ritz? And also decrease the physics time step, change the camera code from fixed update to fixed update, change it a bit. Yeah, maybe we should make these birds a bit less grey. It took me 4 hours to figure out why the birds were so grey, because Unity had turned on some ridiculous fog setting on some nonsense drop-down in a window I'd never even heard of, and it took me 4 hours to figure that out. Oh, Spruce, coding is fun, coding is fun. It's not fun. It's like explaining stuff to 5-year-olds all day or hitting yourself with a brick, and then it runs smoothly. Now my computer is not good, so I can only handle about 100 Boids, but if you've got a big boy, a big huge gaming computer, then maybe you can hold 1,000, 2,000, have a try. So if you want to see the result of all my hard work, click the link in the description. And then I found out Unity had done the same thing 2 years earlier with 1 million Boids.